Hi everyone. Let's continue on to the next section now. With this chapter in particular, it's good to kind of everything you do to review and put it in the context of what you've already done. So let's begin with looking at 4 series, and you should be able to tell me instantly, before I even say anything, whether those converge or diverge. Okay? Can you look at them and see? The first one converges. Recall that the key is that the terms have to go to 0, which they do, 1 over n squared. Those are getting smaller and smaller and going to 0. But just as important, they have to be going to 0 fast enough. They have to be getting small fast enough so that when you add them all up, it still converges to a finite number. And that one does. We compared it with the integral 1 over x squared, which the area underneath that thing from 1 to infinity converged. And so by comparing the areas of rectangles with the area underneath the integral, we could see that this one converged. So it does. This one diverges for a similar reason. First of all, notice that the terms do go to 0, 1 over n. They get smaller and smaller, but they don't go to 0 fast enough. And we learn that by comparing that with the integral of 1 over x. And actually, we did it directly because we actually got that result for 1 over x by comparing it with this. So actually, the most direct way we did this was just by listing out the terms and then grouping them together in groups that were always twice as big as the previous group in size. And all of those groups were greater than 1/2 in size, and so you could go on like that as long as you wanted, and so that sum goes off as big as you want. Okay, so that's called the harmonic series. This one here, does that converge or not? Hopefully you look at that, and by this point in your mathematical career you can say, oh, I can see that as n goes to infinity, these terms individually are going to get closer and closer to 2/5. Right? As n gets big, they get closer and closer to 2/5, and so the terms are not going to 0. And if the terms aren't going to 0, then you know for sure that it's not going to converge. You can just think of it as adding 2/5 plus 2/5 plus 2/5 over and over again, and it's going to diverge. Finally, this one here, you look at that and you say, well, that's kind of complicated looking, but here's the essence of it. You essentially forget about the constants and things like that. You essentially have an n on top and an n to the 5/2 down below. And that is, let me get rid of this and just say that. That's what you've got. And of course, that's the same as 1 over n to the 3/2. And we proved along with these that for any power of n here, we usually call this the p-test because we think of this as n to the power of p. For any value larger than 1 in size, this, when you add these things up, it's going to converge. And n to the 3/2 is larger than 1, so what's the key? These things do go to 0 fast enough. This thing acts like this. We called the limit comparison test, where we compared this with this by just taking these things here and saying, hey, they act basically like these. And if you take the limit of this quantity as n goes to infinity, you're essentially going to get, you're just going to get 2. It's going to approach 2. And the point is that since these things converge, and these are twice as big, they're going to converge. Okay? You can bring the 2 out of the summation sign. So that one converges. Okay? So that's a good review, and I'll keep doing this as we go. At some point, I'll just do a whole lot of problems for you from a sheet I have. So now, here's what we're going to do. We're going to say, what happens if I suddenly make the world a whole lot more complicated looking by doing this instead? I'm going to take each of these, which are, notice they're always positive, and I'm going to alternate them so that now they alternate in size. The first one's positive and the second one's negative, or however you want to do it here. It doesn't really matter. -1. this. Okay, here I'm going to, let's see, this one I'm going to start, obviously has to start at 1. This one can start at 0. This one can start at 0. Since I'm starting at 1, I don't know, I always like the first one to be positive, so I'm going to write a n plus 1 there so that it's the first one is positive. It's just, you know, you get set in your old ways. Doesn't really matter. So anyway, the key point is that these things are going to now alternate in sign. This thing here is going to be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. This one is going to be what? 1 minus 1/4 plus 1/9 minus 1/16 plus 1/25 and so on. So how does alternating the sign affect things? How does that affect things? Well, let's look at this piece by piece. First of all, this one is still going to diverge. Why? Because these terms are still not going to go to 0. They're going to alternate between 2/2 and -2/2. So the terms don't go to 0. I'll just say, hey, here the ANs don't go to 0. And since they don't go to 0, we had a result earlier on in the couple lectures ago, a couple lessons ago, that this thing diverges. So that one is set. Okay? Let's look at this one next. We saw, and this one's going to fall in right with it, we saw that this thing here converged. And doesn't it seem reasonable that if when you add them all up, all of them being positive, if that converges, if that gets closer and closer to some finite number, that if you just let some of them be positive and some of them be negative, that should also converge. It's going to converge to a smaller number, but if these get small fast enough, these are going to be getting small just as fast, and not only are they getting small, but they're kind of fighting against each other. Some of them are positive and some of them are negative. So they're not only getting small, but they're fighting. They're not all moving in the same direction. So if you think of 1 over n squared, what do? Here's 0, here's 1, and now you add, or this one here, you're going to add a 4th, and then you add a 9th, and then you add a 16th, and you keep adding smaller and smaller numbers, and it never gets beyond whatever the limit was. Well, I think actually the limit is pi squared over 6, I might have mentioned to you. So it's going to get closer and closer to that if they're all positive. If they're now if they alternate positive negative, now what's going to happen? You start with 1, and then you subtract a 4th. So after subtracting a 4th, now you're there, and then you add a 16th. So now you're there, and then subtract. You can kind of see what's going to happen here. It certainly seems like that one is going to converge as well. So let me actually prove this result. And I've actually given you a little more than you bargained for here, but here's the theorem. It says this. If this thing converges, then this converges. Okay? So if you slap on the absolute values, if you slap the absolute values on this, you're going to get this one, of course, right? You make everything positive, and it turns into this one. And we know that this one converges. So what does this theorem say? It says since this thing converges, all of them being positive, then if you allow some of them to be positive and some to be negative, then that's also converge. So it certainly seems reasonable. Let's go ahead and prove it. Okay? It makes a lot of sense. But this is actually one of the more clever proofs I've ever come across. I'm going to have to look at my notes just to remember how it goes. Okay? First of all, do you agree that this is the case? Each one of these a sub n's, we're looking at basically this sort of a situation now. Actually, a sub n itself can be positive or negative. So I'm thinking of this entire thing as being an a sub n. So there's my a sub n right there. It itself could be positive or negative. So a sub n is always going to be between its absolute value and the negative, right? This is always negative, this is always positive. It's going to be one or the other depending on whether it's positive or negative. So that's the case. So if you add absolute value to everything, you're going to get what? You're going to get that. Agreed? You're going to get that. And now I make use of one of the theorems that we already have. We're assuming that this thing converges. And so since this thing converges, if you multiply it by 2, that's not going to change anything, because whatever this converges to, if you multiply it by 2 outside here, it's just going to converge to twice the value, and you can bring that 2 inside and it doesn't affect anything. So this will also converge. So I'm going to say, I'll write it all out. Since this thing converges, I'll write CONV for converges. I'll just spell it all out. 2 times that thing, which is equal to 2 times this, that converges. Okay? And since this thing converges, and these are all less than or equal to these by our I forgot what we called it, but it was some sort of a comparison test, this is going to converge. Okay? Because each one of these things is less than or equal to these, and these, when you add them all up, that converges, and so when you add up all these things, it's going to converge to some finite number. So that converges. So that's true, and now you get the result. So here's what we're after. This thing right here is equal to, and again, I need to watch this one. Okay, it's going to be AN plus, like that, minus this. Whoops. Do you agree that's the case? Here's a fancy way of writing this, because I just added and subtracted the same thing there. That's true. And now this thing can be broken up into 2 things. As long as these things individually converge, you can break it up into the sum of the 2 of them. And we know that this thing converges, and we know that this thing converges. That's what we're assuming. And so since these 2 things both converge, you can bring them together, and that's going to converge, and that's just equal to this. So this thing converges. Boom. There you got it. So as I say, it's kind of a clever, for whatever reason it is for me anyway, it seems like kind of a clever proof that proves an obvious result. It seems obvious that if you make everything positive, that converges, then if you allow some of them to be negative, that's going to converge. Okay, so anyway, so that takes care of this one, and it also takes care of this one, right? So if you make everything positive, those converge, and so if you alternate them and make some of them negative, that's going to converge as well. So that takes care of both of those. Here's the one remaining. What about this one? What about this harmonic series, which I guess it's no longer a harmonic series because it's alternating now. Maybe you call that an alternating harmonic series. It would seem like a reasonable thing to do. But is that going to converge or not? Here's what we know. We know that if everything is positive, then it doesn't get small fast enough, right? They keep adding up together. So let's draw a picture. Here's 0. Here's 1. If these were all positive, let's just look at this first. 1 plus 1/2 plus 1/3 plus 1/4. So you take 1 and now you add 1/2 to it, and you're right there. Then you add 1/3 to that, and you're right there. Then you add 1/4 to that, and you're right there. Each step is going to be smaller than the previous step, but what's the key? The key is you can keep taking chunks that add up to greater than 1/2, so I know that if I want to eventually get past 2, I'm going to eventually get past 2. If I want to get past 3, I can add up enough of them to eventually get past 3. So this thing is going to head off to infinity very slowly, but it's just going to get arbitrarily big. This thing diverges. However, what happens when instead of letting them all contribute positive, if now they alternate? So here's 0, here's 1 right here. Okay, let's see what happens here. Start with 0, and then, we'll start with 0, and here's 1. So here's 1, and so there's your first. There's what happens when you just take the first one. Now you take 1 minus 1/2. So what's this partial sum going to be? 1 minus 1/2. That's going to be down there. That's going to be what happens when you, I'll call this S1. That's the first sum. Here's the sum of the first 2, which is S2. Now what? S3 is what happens when you take the sum of the first 3, which is going to be up here someplace. You add a third to that, and it's going to be up here. So here's S3. So that's this one right here. Now you have S4, which is what happens when you add the first 4, and that's going to be what? You subtract the 4th from this. This jump here was a jump of a third, and now you're going to jump back a 4th. So I'm going to jump back a 4th, so I'm going to be right there someplace. So here's S4. Okay, there's a jump of a 4th. Now you do what? Now you add a 5th, and again, this jump here was a jump of a 4th. It's not going to be that large of a jump. So if you jump up here, it's going to be S to the 5th. And can you see what's going to happen? Where's the 6th sum going to be? It's going to be right there. S6, S7th is going to be right there, and so on. So here's what we see. All these even sums keep increasing, and they're bounded by any of these odd sums, so they're an increasing bounded sequence, so we know that these things converge. Similarly, this is a decreasing bounded sequence, so we know that those things converge. So both of these are converging. They both have to converge, and so basically the idea, the picture does as good of a job as anything. Okay, the picture does as good of a job. Is you just realize where do they have to converge to? Here's some limit in between there that these are climbing up towards and these are climbing down towards, and you just keep jumping over that each time. And so basically what's happening is that these are converging up and these are converging down, and they're getting closer and closer. Why do we know they're getting closer and closer? Here's one of the keys. These things here, again, are going to 0. So each jump has to be smaller than the previous jump, and not only smaller than the previous jump, the jumps are getting closer and closer to 0. So once you have your limit there, given any little epsilon neighborhood around that, eventually all of your jumps are going to be within that little epsilon neighborhood, and you're going to stay right in there. So one of the keys for this thing working is that these things right here, let me just call it the a sub n's. I'm gonna write it like this now. I'm gonna write it like this, where the a sub n's themselves are positive, and then I'm gonna take them and alternate them just like I did here. Notice these are all positive, and then I take and I alternate the signs by putting this here. Okay, so this is called an alternating. I'll just write it right up here. It's called an alternating series. Okay, it's called an alternating series, and one of the keys is, in order for these jumps to get smaller and smaller and smaller, the jumps themselves have to be getting closer and closer to 0. Okay. The other key thing here, notice, is that each jump has to be smaller than the previous one. See, I really should have put that there first. Let's first say that. In fact. Let's say this, that each jump, here's the size of each jump. Each jump has got to be less than or equal to the previous jump. So every time you jump, you go a smaller distance. Okay, you're just like a door that's swinging back and forth. So you're going to smaller and smaller distance, and then not only is each one smaller and smaller, but they get closer and closer to zero. If these jumps, let's just think of it like this. If you were jumping back and forth, and these jumps did this, so you went here, and then here, and then here, and then here. Each one is smaller than the previous one. And then here, and then here, and then here, and then here, and then here. Each one is smaller than the previous one, but if there's still a big gap between these two, then there's no limit. It's only when this gap goes down to zero that you have this limit in between. So that's what's key. Key is that not only is this the case, but also these things are going to zero. And what I like to do, just make sure that I've got everyone on board here. Yep, okay. What I like to do is to combine these two things and write it like this. These two things combined, I like to write it like this. Some authors do this. And so this means two things. It's actually telling you three things. It's telling you that, that the terms are going to zero, the limit of them is zero. It means that they're going monotonically to zero. Each one is less than or equal to the previous one. Okay, so they're not bouncing around zero like this. Okay, the terms a sub n themselves are heading straight to zero, and since they're all heading straight to zero, then it's also implied that these terms have to all be all the terms have to be positive, or at least non-negative, right? Because if you're heading down to zero, then the terms themselves have to be non-negative. So it really captures all three of these things in this one little symbol here. So that's the way I like to write it. Okay? So this is true for any series, any series that has the same property as this one, it converges. So here's our theorem. It's called the alternating series test. Okay, and here's what it says. It's kind of easy to say. It just says that if these things are monotonically approaching zero, then this series converges. Okay, called the alternating series test. Say if those things are monotonically approaching zero, then when you slap on the negatives on every other one, that thing's got to converge for the same reason that this one does. Okay? There you go. Okay? So, so notice that now we have kind of three different ways, three different things that can happen to a series. The series can either diverge like this one, or it can converge like this one because the terms are getting small fast enough, or it can converge like this one because while the terms are going to zero, they're not going to zero fast enough to converge all by themselves, but when you allow them to compete with each other so that some are positive and some are negative, and they alternate and they compete back and forth and they cancel each other out, then it converges. So let's give a definition here to kind of capture all three of those things. We already have what it means to diverge, but here's what we can say. If this series converges, so you make everything positive, so it's not getting any help at all from negative numbers. Everything is non-negative, but it still converges, then we say that this series converges absolutely. Okay, absolutely. There's no ifs, ands, or buts about it. It's not conditioned or reliant on the fact that these things are canceling each other out. It says, heck with all you negative signs, I don't need you. I don't need you. I'm going to converge no matter what. This thing converges absolutely. Okay? Absolutely. Okay? On the other hand, if this thing diverges, but the original series converges, which means the only reason this one is converging is not because the terms are getting small fast enough, but it must be because they must be canceling each other out. Some of these must be negative and canceling out others that are positive. And so it's only on that condition. It's only on that condition that this thing is going to converge. Then we say that this thing converges only on the condition that you have that cancellation. So what's a good word we use? How about conditionally? Yep, there we go. Conditionally. Conditionally. Okay, there you go. So now, given any series you see, you'll want to differentiate between three different possibilities. Does it diverge? Does it converge conditionally? Or does it converge absolutely? Okay? And that's the idea. So let's try some and just give you some practice now, determining what's what. So now almost everything I put on the board, I'm going to throw on those negative signs, and you're going to have to choose between three different options. Okay, so let me just give you one here. How about 1 over, let's go this one. Okay, that one right there. What does it do? Well, hopefully you look at that and you say, these, you just have to understand them. Just have to understand them. So here's what I just say. Hey, heck, this thing right here is going to be always less than or equal to this thing right here, right? Because these are bigger. And this thing right here converges absolutely. Okay? And so basically, I guess, yeah, I mean, it converges from the p-test. And so this thing right here is going to converge absolutely. Let me do it a little bit different. Let me just go like this. I'm going to say, I'm going to go like this. I'm going to write it like this, n cubed plus n. If I slap on absolute values, that's equal to this. Right? If I slap on absolute values, I get that. And then I can say this thing right here is less than or equal to this thing right here. And then I can say since this thing converges, these are all greater than or equal to 0. Since this thing converges by p-test, okay, that means that this thing converges by comparison test. I'm comparing it with another one that already I know converges. And now I can say that what? I can say since this thing converges absolutely, it converges. Okay? So I know I can say two things about it. I can say it converges, which it does, and I can also say it converges absolutely, because it doesn't require those negatives in order to make everything cancel out. Okay? What if this were a square root of n instead? Okay? Now I would look at that, and again, you need to just be able to just see the result. You have to just become familiar enough with the behavior of these things that that's what makes this stuff fun. Is you're not like taking derivatives where, okay, just here's a mechanical thing, take the derivative. No, you have to understand it. You have to understand the landscape. So I look at that and I say this. I say there's different ways to do it. I first of all notice this. I noticed that those things are going to go monotonically to 0. Agreed? As n gets bigger, they're just going to get smaller and smaller. So I know that it converges. I know that it converges one way or another. It's going to converge. It's going to converge by the alternating series test, alternating sign test. What do I call it? Alternating. I forgot the word. Alternating series, I guess. I forgot what it's called now. Okay. Anyway, by the theorem I just had up there, we know it converges. But I want to know, does it converge absolutely or conditionally? Okay, does it converge absolutely or conditionally? At least it converges conditionally, but does it converge absolutely? Well, let's check it out. If I slap on absolute values there, I'm going to get this. Okay? And I look at that and I just say, there's a couple ways to do it. I can say, here's one way to do it. I can say square root of n plus n is less than or equal to n plus n, right? Because this is going to be bigger than this, which is equal to 2n. And since that's the case, 1 over this is going to be greater than or equal to 1 over 2n. Agreed? And of course, all these things are positive now. Let me just stress that. Okay. I guess I need to put it over here. Okay. So these things are greater than or equal to 0. And then what do I say? I say, well, hey, what about this thing? I can bring the 1/2 outside. And I look at that, there's my harmonic series. I know that this thing diverges. So that diverges, and so since when I add up all these things, it diverges. When I add up all this thing, all those, so I can say that's going to diverge. Okay? So it converges because of the negative alternating sign. Otherwise, they don't go to 0 fast enough, okay? They don't go to 0 fast enough. So that's one way to do it. Another way to do it, and this one is my favorite test. I just look at this and I just say, heck, what's the most powerful thing there? The most powerful thing is the n. That's the thing that's getting big fast enough. So I just look at that and I say, that's really going to act like 1 over n. It's really going to act like that. This is really not going to pay any, have much of any effect as n gets big compared to this. So I look at that and I say, okay, what happens to that limit? I can flip the n up and I get this, and then I can divide both the top and the bottom by n, and I'm going to get 1 over square root of n plus 1, and that goes to 1. So that goes to 1. What does that tell me? I know that since this thing diverges and the ratio is 1, that means that in the long run these things act like these, and so that tells me that this thing is also going to diverge. Okay, that's the idea. So so there you go. Let's see, a last thing that I'll mention with regard to this, and as I say, as I go from now on, I'll just keep doing more and more problems, because you just get rich in the number of problems that you can do, and that's all part of the learning game. But as we mentioned before, sometimes you not only want to know whether anything converges or not, you also, if it does converge, you want to know what it converges to. And sometimes we can get an exact answer, but quite often in mathematics you can't get an exact answer. The most you can do is get an approximation. And so the proof that we had of this thing, again, these are assuming that the ANs are all greater than or equal to 0 here, so this is an alternating series here. Each one is alternating positive, negative. Okay. Let's look at the picture one more time and see once what happens. So a sub 0 is going to be the first thing, right? If n is 0, you're going to get 1 times a sub 0, and that's a positive number. So there's a sub 0, and I'll call that s sub 0 as well, which is I'll call that the zeroth sum, the sum of just the zeroth thing. And then what happens when you take the next one? Let's go ahead and write them out here. You're going to get a naught minus a1 plus a2 minus a3 plus a4 minus a5 and so on. What happens when I subtract the first thing? So right here is going to be s1, which is equal to what? A naught minus a1. And then when I add a2, I'm up here again, right? So here's s2 right there. And then I subtract a3, and I'm right there. So here's s3. And then I add a4, and I'm going to be right here. Whoops, I guess I'm writing these down below. That makes sense. s3, s4, and so on. So what's happening? As I mentioned before, these are going down to the limit. These are going up to the limit. So the limit, the thing that this whole thing is converging to, call it L. Let's call it capital S for the sum. Okay, so there's the sum. That's what it's converging to. Notice that every time you add the next one, you are jumping over that thing, right? Because here's S4. Now you've got to jump over it because S4 is right there. S5 has got to be on the other side of it because these have got to be going up towards the limit. So S5 has got to be right here. S6 has got to be right here. S7 is going to be right here, and so on. So every time you do the jump, you jump over it, which means that the jump from S6 to S7, here's the key, the jump from S6 to S7, let me add these out again. Let's see. Plus a sub 6 minus a sub 7 plus a sub 8 and so on. How did you get from S6 to S7? The way you got there was by subtracting that thing right there. Agreed? So this thing right here took you from where to where? It took you from here to there. So this term right there, you went past the limit to this side. So in other words, I don't want to make a simple thing hard. In other words, wherever you stop, if I were to stop right there with S sub 7, how close am I to the actual limit? If I were to stop right there, how close am I to the actual limit? Well, a sub 8 takes me past it. See there? There's S sub 8 right there. So in other words, as soon as I stop right there, how close am I to the limit? I'm at least that close. That's the key. Okay? That's the nice thing about alternating series. Wherever you stop, the next term tells you how close you are. Okay? You're at least that close. And so it's kind of a nice way to be able to very quickly say, wherever you stop, I know I'm at least this close. Okay? So that was different from when we added up positive things, right? If you add up positive things and you start with 0, here's 1 plus a fourth. Here's S1 right here, here's S2, here's S3 right there. You stop someplace, and this whole thing is going to keep going on like this. Maybe there's your final sum. And how close are you to the final sum? Well, it takes some doing to figure out how close you are to the final sum. With this thing, we were able to do it. With this, we were able to do it by looking at the integral. But in general, it takes a little work to try to figure out how close you are. But if you have an alternating series, then you know wherever you stop, you know that you're that close to the final result. Okay? Very good. So this is again good stuff. In the next lesson, we will go back to the geometric series. Remember what the geometric series is? Looks like that. And we will find two generalizations of the geometric series, which are two of the most powerful, important theorems in the whole theory of sequences and series. So that's coming up.